All right, this is the start of a new chemistry series. Basically, we're just going to solve every single chemistry paper one paper from 2016 onwards. So hopefully this will be a bit fun. We're just going to start with this here, May, June 2020. I'll be dividing each video up into 10 question parts. So yeah, first 10 questions for this video. Let's just get started, I guess. Yeah. Write your name in pen. Okay, write in soft pencil. Yeah, I don't know if this is soft pencil. Anyway, let's just get started. These are the instructions. All right, let's start with this. All right, so for each question, there are four possible answers. Use of the data booklet, this thing right here, we have on our separate tab right over here. So, yeah, all right, let's go. All right, so ethene can be oxidized to form epoxy ethane. Okay, so you basically have to know one. All right. So you have C2H4 gas plus 1 half O2 gas goes to that. Okay, so first things first, you know that since the enthalpy change is negative, it's an exothermic reaction, so it's a good habit to put heat on the product side since it's exothermic. And what are they asking for? Let's see, the greatest yield of epoxy ethane. Okay, so when you're solving this question, the first thing you want to look at is the number of moles of each gaseous compound. So you can see on the reaction side, there's 1 mole of C2H4 and 1/2 moles of O2. And then you also have 1 mole of epoxy ethane. So overall, you have 3/2 moles of gaseous products and only 1 mole of, well, yeah, sorry, 3/2 moles of gaseous reactants and only 1 mole of gaseous products. So in that case, if you were to increase the pressure, the equilibrium would shift to the right. So they're saying how to get a larger yield, first of all. Like I just said, if you increase the pressure, since there's more gaseous moles, there's more moles of gaseous reactants than products, you know that the equilibrium would shift right. So in this case, you'd want to have high pressure, not low. So you can immediately rule out choices C and D. And then let's move on to the next part, which is regarding the temperature. So if you were to, basically you're choosing between 100 and 200. So you can think of it as basically being a lower temperature or a higher temperature. So when you're choosing a higher temperature, your heat would increase, right? And because the heat increases, what this heat will do is it'll shift to the left. And we don't want that because we want to have the greatest yield of epoxy ethane. So in that case, we'd want to have, instead of the arrow going up, we want to have an arrow going down, which would mean we'd want the lower temperature. So the 200 options would be wrong. So in this case, your answer choice would be A, which I do believe is correct. And yeah, it is correct. All right, question 2. Cobalt can form the positive ion this, okay? So we already know that there's going to be 6 ligands here, 4 NH3 ligands and 2 Cl ligands. So what is the oxidation number of cobalt in this ion? Okay, so what this will look like is, here, wait, let me just move this up a bit. This looks like this. So you have the cobalt ion in the center, and you have dashes here. Let's see, NH3 here, one more NH3 here, like that, and then another NH3 here. And then you'd have a Cl and a Cl. And obviously you could have stereoisomers of this, but we're not going to focus on that right now since we're just looking at our ion charges. So NH3 is a neutral ligand, so you know that that would have a 0 charge, and Cl typically takes on a -1 charge when it forms ions, so you can put minuses on both of these, you can put zeros on these if you want. So in that case, you already know that overall, just with the ligands, you have a charge of -2. Now, the overall charge of the ion is positive, which is basically saying it's +1. And how you would calculate this is the charge on the cobalt ion, let's say it's X, plus the total charge of the rest of the ligands, so in this case that would be -2, would equal the overall charge of the ion, which is, in this case, just 1. So you'd have the charge on the cobalt ion is +3, which is answer choice C, and yes, that is the correct answer. So yeah, again, remember that NH3 is a neutral ligand and that Cl typically takes on a -1 charge. Ignore the sound in the background, that is the sound of the oven going off. Anyways, let's move on to the next one. When considering one molecule of ethene, okay, which row describes both the hybridization of the atomic orbitals in the carbon atoms, okay, and the overall bonding. Okay, so what I would do is I'd start off by drawing it out. So let's see, it it looks like this if you were to draw it out completely. Again, you can also just technically just draw a line if you want to draw a skeletal structure. But anyways, how you'd want to go about this is just count the number of single bonds. So 1, 2, 3, 4, and then one for each double bond or triple bond if we had one. Just take one sigma bond out, and then the rest will be pi bonds. So in this case, there were 5 lines overall for that. So there's 5 sigma bonds, and in this case, there's one of those, so there'd be 1 pi bond. So overall, you know there's going to be 5 sigma bonds and a pi bond, so it can't be this or this. So in that case, we can rule out answer choice A and C. Now let's look at the hybridization. Okay, let's use black again. Again, there are 3 domains, so 1, 2, 3, and you know the rule goes SP2, 3. So in this case, it's just SP2. So it's SP2 hybridized, therefore SP3 would not be it. And again, you can know that because this is a planar molecule, and planar molecules typically all have SP2 hybridization, not SP3, which would be tetrahedral. So again, you can rule out D like that, so your answer choice would be B, and that is correct. All right, moving on. 10 centimeters cubed of ethane is burned in 45 centimeters cubed of oxygen at a pressure of that and a temperature of that. Okay, complete combustion, so we know everything reacts, takes place. Okay, so the first thing you'd want to do is set up a reaction. So combustion, okay, ethane is C2H4, well, H6, right? Because it's CnH 2n plus 2. That's the formula. And you know that it reacts in X6 oxygen. Now, I'm going to leave that blank for now. And it goes to carbon dioxide and water always. So when you know this, take a look at these 2 numbers right here. So there's going to be 2 carbons. So the only way you can get a carbon is through CO2. So you know there's going to be 2 CO2s. And the only way you get H's is through water, which would be 3 H2O, since the coefficient of the thing here is 2. So you have 6. And overall, that means you have, let's see, 2 O2 will give you 4 oxygens, and 3 O would give you 3 oxygens. So you would have 7 halves O2, that way you get 7 oxygens on both sides. And let's see, the question is asking for the total volume of gas present, okay, measured under the same conditions. All right, so then the conditions really aren't that useful for this one. So let's just take a look at this stoichiometry equation and go on through that. Gaseous compounds, you can treat them with volumes instead of moles if you want, since gaseous compounds, when they are ideal, typically they take up the same volume. So yeah, just know that. So using that, 10 centimeters, we use 10 as the moles, you know, moles in quotes, but anyways, 10 there, then you would have 35 here, and you would have, 35 there, and then 20 here, and then 30 here, because again, since there's 10 for this, you're just multiplying by the coefficient for each other one. So 7 halves times 10 is 35, 2 times 10 is 20, 3 times 10 is 30, and so on. So we know that initially that was 45, and then finally that would be 50. So overall, your gaseous volume increases by 5. So you could technically just say, well, there was 10 of this and 45 of this. So 10 plus 45 plus 5 is equal to 60, which will give you answer choice D, which is correct. But if you wanted to use it more logically and like more properly, instead of just doing that kind of logic, you could say that since 10 moles, all the volume of ethane was used up, and only 35 of the oxygen was used up, you could say that overall the reactants used were, let's see, 10 and 45. So you used up all 10 and you only used up 35 of this. So you're left with 10 centimeters cubed of oxygen. So, and set that aside for now. And then you know that these 10 and 35 values gave you 50. So in that case, 10 plus 50 would give you 60. Again, same result, but this one's like how you do it if you were to explain it to someone. But yeah, either way, answer choice D is correct. Moving on. 2 reactions are shown. You have, let's say, H2 gas going to 2H. Okay, so you know that that is bond energy probably, because you're not really doing atomization, because atomization would only have 1 mole of gaseous products. So, okay, molar amounts are used. Okay, oh, and that's a combustion reaction. XSO2, CO2. Yeah. Okay, so how can the 2 energies associated be described? Oh, okay, so like I said, it can't be enthalpy change of atomization. Oh my god, it just changed. It can't be enthalpy change of atomization, because if it were to be that, you need to have 1/2 H2 gas goes to 1 mole of hydrogen gas because, well, not elemental, but just one hydrogen atom, let's say, because you need to have 1 mole of the gaseous product. So this would just be bond energy because what you're basically doing here is you're having this HH bond and you're splitting it to make 2 H's. And that would be that. So again, bond energy, so that's fine. This one right here, that is not formation. Formation, you'd be forming a product from the natural things, but again, you're combusting it in excess oxygen, so this would be a combustion reaction. So we know that's combustion, and that, whoa, not that one. So we know it's one of these two. So again, using your logic, now that you've crossed out A, B, and D, your answer choice is C. And I believe that is the right answer. Yes, it is the right answer. Moving on. Let's use a different color this time. The diagram shows the Boltzmann energy distribution curves. Okay, so you know that the axes are going to be energy and the number of particles with that corresponding energy. So, okay, at 2 different temperatures, and which one is at the lower temperature? Okay, so energy is directly proportional to temperature because if you think about it, right? As temperature increases, your energy is going to have to increase as well because, again, the molecules are just going to move faster. So, using that knowledge, if there's a higher temperature, right, more molecules would have a higher energy. And that's the case in this case because more of them are there. So your lower temperatures are always going to be the peaks to the left. And in this case, you have this peak right here. So, sorry, I drew the things wrong. This side is the number of particles, and this side is the energy. My apologies. So, you know that this has the higher energy and that has the lower energy. So, yeah. Let's see. Lower temperature. Oh, wait, no. Oh, no, I'm right. Yeah. Okay. Sorry, I'm confusing myself. So, lower energy because, again, this side, as you go this way, the energy increases. So, C is less than D. So, obviously, this peak right here is going to be the right one. And you know that since most probable energy right here is calculated by looking at the number of particles that are most likely to have that, the higher the peak, which is, again, these points right here, that is your most probable energy value, and that is where the most particles will have that energy. And that is the whole purpose of these Boltzmann distribution curves. So, again, it wouldn't be A because that's just the number of particles, and C would be the right answer because that is your most probable energy. Right. And I think that's right. Yes, that is right. Okay. Moving on. What are the units of Kp? Okay, so immediately, you know that Kp would be, let's see, you have H2 gas, so whenever you're doing this, it's just like drawing the Kc values, but you're using pressure instead of concentration. So pH2, PCO, CS right here is a solid, so you wouldn't include it, you just include this H2O, so pH2O. Looking at the units, each of these are going to be in pascals, looking from the answer choices here. So you have pascals times pascals divided by pascals, because again, each of these pressures are just going to have a unit of pascals. So crossing those two out, you're left with pascals, so that would be answer choice B. And yes, that is the correct answer. All right, moving on. Question 8. Okay, it says, in this question, you should use changes in oxidation numbers. Ooh, okay. So this is a balancing question. Okay, acidified potassium dichromate, okay, can be used to oxidize a solution of V2. Okay, so the first thing you want to do in these types of questions is identify the charges on each of these separate ions that are like actually going to be used, right? So you know that they first of all mentioned chromate, so you're going to need to look at the charge of chromium, and you're going to need to look at the charge of vanadium. So in this compound right here, oxygen always takes up a -2 charge. So that's 3 times -2, which is -6. Your overall charge is -1, so you're going to have a +5 charge on the vanadium ion there. And you know here, charge is 3 plus. Well, let me just rewrite that. That's not ideal. And then looking at these V2 plus, this is, whoa. Sorry, this iPad is being weird. That's a +2 charge. And again, 7 times negative 2, so that's negative 14. There's a negative 2 charge, so you're going to have to make it positive 12, right? Because, again, negative 2 plus 14 would give you 12. So each of these chromium ions would have a charge of plus 6. So looking at the things, the chromium charge goes from positive 6 to positive 3, which means that it's going to lose 3, well, it's gaining 3 electrons. But notice how there's 2 of these chromium atoms per compound. So if we assume A to be 1 for now, you know there's going to be, oh my god, you know there's going to be 6 electrons corresponding. And if we do that to the other side, notice how vanadium only has a plus 5 charge going from plus 2. So if you were to calculate that, that's again 3, right? Because 5 minus 2 is 3. So you're going to have to incorporate these 6 electrons in, you're going to have to make this part right over here a coefficient of 2. And then using logic from that, if you're having 2 vanadium atoms overall, you're also going to have 2 here. So then your A to B ratio here would be 1 over 2. And that is answer choice B. And the answer is indeed B. Okay. So again, when you're looking at these, just balance it. First find the number of electrons, and you can do that by, again, analyzing the 2. Typically, they're transition metals. So looking at the 2 transition metals, and then looking at the total number of electrons, and then balancing the coefficients that way. These are pretty tedious too, so I suggest coming back to them if you're not good at doing this, because these are pretty time consuming, and you're not really given that much time. Moving on. A sample of argon gas has a mass of 0.2 grams. Okay, and a pressure of that and a temperature of that. Okay, so this is probably PV equals nRT. What volume does the gas occupy? Okay, so this volume, again, PV equals nRT. And you know that N is just mass divided by the molar mass. So PV is equal to M over MR times RT. So in this case, let's see, you're given pascals, you're given, 12 degrees Celsius, you add 273 to that to convert to Kelvin, so that would be 285 Kelvin. And again, the molar mass of argon, oh my god, I do not like how it switches. The molar mass of argon, we need the data booklet for this, so let's move on to the data booklet. It is on the last page. Oh my god, we have to scroll through 20 pages. Never mind. Okay, so it's right here. Argon is right here, 39.9. So using that, we say that the molar mass of argon is 39.9. And we have all the values we really need at this point. So let's see. Pressure, which is 100,000, times our volume, which is going to be in meters cubed here because we're using pascals, is equal to M over MR, which would be, let's see, our mass is 0.20 grams, divided by our molar mass, which we found that is 39.9. Our R is going to be 0.08206 in this case, times the temperature, which is in Kelvin, 285. So if you were to find that out, you would get the volume is equal to, let's see, let me plug that in the calculator real quick. There's a lot of values. Okay, you get about 0.000119 meters cubed. Well, it's like 118 something, but you don't really need to know that. Looking at the answer choices, this one is a really good candidate. And again, if you want to convert, just every time you go up by a 10, like by 10 units basically. So if you were to convert meters cubed to decimeters cubed, just multiply it by 1,000, because if you want to see the conversion, meters cubed, you're basically doing 10 decimeters. Well, no, sorry, wrong side. 10 decimeters cubed divided by 1 meter cubed. So you'd multiply that by 1,000, so that's 0.119 decimeters cubed. We want centimeters cubed, so that's just 119 centimeters cubed by, again, doing the 1,000 thing one more time. So our answer choice should be D, and yep, it is indeed D. And looking at this next one, in which pair does each species have the same number of unpaired electrons? Ooh, okay. So for this one, you'd probably want to look up the Boltzmann. Well, no, not Boltzmann. What is it? The energy levels. So I'm just going to do it really small here. aluminum. Okay, we need to go back to this table. Aluminum right here is in this group, right? So you have the electron configuration would be 1s2, 2s2, 2p6, and by the way, here's how I'm going in. 1s2 would be here, 2s2 would be here, 6 more electrons would give you 2p6, and then this would be 3s2, and then that would be 3p1. So aluminum would just have, okay, right here, aluminum would just be 3p with 1 electron versus, let's see, copper 2 plus. Okay, so copper and chromium, we have to keep in mind here. When you're doing Boltzmann distribution, electron configuration diagrams, you always have to make sure that when you're doing copper and chromium, these ones will lose their 4s2 ones first, and also that transition metals will lose these two 4s ones first as well. So keeping that in mind, moving on, copper 2 plus. Well, we already know copper's over here. So if this is the end of the 4s2 zone right here, then we know that there's supposed to be 9 electrons, and it's 2 plus, so we're taking out 2. So in that case, you would have 9 electrons overall. So these are in the 3D orbital, so drawing that out. Let's see, 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So overall, there's 1 lone pair and 1 lone pair. Well, not lone pair, but a lone electron. And that means that this ratio right here is 1 to 1. So I think we do have found our answer, 1 to 1. So that's a check. Should be A, but just in case, let's get the other answer choices as well. Calcium would be what? Calcium is, oh, right here. So that would be the 4s2. So this one wouldn't even have a lone pair, because, whoa, I just closed that out. Give me 1 second. Yeah, let's go back to this. Okay, calcium, again, is right over here. So that wouldn't even have a lone pair. That would just be that. And at the same time, what's our next one? Chromium. Okay, well, let's just wait for us. Okay, chromium 3 plus. This would be, again, it's transition metal, so it's probably going to be in the 3D orbital here. Okay, chromium 3 plus. So it has 24 electrons overall. It loses these two, and then it loses another one. So it'll be over here overall. So 1, 2, 3 electrons. So 1, 2, 3. So you're going from 0 versus 3. So this is not correct, right? So we can rule out that answer choice. Okay, calcium and nickel. We all know calcium from the above question, so let's do that. Versus nickel 2 plus. Okay, nickel 2 plus is this, and again, it loses the 4s electrons first, but keep in mind that this nickel only has 1 4s electron, because again, chromium and copper are the only exceptions. So knowing that, if it loses 2 electrons, then it would be over here at 27. So that means there are 7 electrons overall. 1, 2, 3, 4, 5. Again, 3D. 1, 2, 3, 4, 5, 6, 7. So in that case, the ratio is 0 to 3. So again, this one's not right. So that's another one eliminated. And then our last one here, Fe3 plus and O2 minus. Fe3 plus. Okay, looking at our 3D orbital again. Fe3 plus, right over here. Okay, so Fe3, okay, it loses 1 4s and then 2 more. So it's right over here. So 4 electrons. So 1, 2, 3, 4 versus our O2 minus. So oxygen with 2 electrons gained would be over here. So it would have its 2p orbital completely filled. So again, 2p, it would go like this and be completely filled. So it's 4 to 0. So again, this one's not correct either because we want the ratio to be the same. So our answer should be A, and it is A. Okay, sweet. All right. Just because 11's on this page, I'll do this one too. Why not? A sample of solid ammonium chloride. Okay, so that would be NH4Cl, because NH4 is ammonium, chloride, Cl. Decomposes on heating, so you have solid ammonium chloride, so that's NH4Cl, ammonia gas, that's NH3, and hydrogen chloride, that's HCl. Right? And if we look at the stoichiometry, it should just be 1, 1, 1, So that is correct. All right, so a total of 2.4 times 10 to the 21 molecules of gas are formed. Okay, that's weird. That should be R, but anyways, not going to question it. How many hydrogen atoms are present? All right, so what you want to do is analyze each of these separate products on their own. So if you know that there's going to be 2.4 times 10 to the 21 molecules of gas, just take your overall moles of gas, because these are all assumed to be ideal, and divide it. So 2.4 times 10 to the 21 divided by 2, you get 1.2 times 10 to the 21. And then that means that now you have 1.2 times 10 to the 21st molecules of NH3. And at the same time, you also have 1.2 times 10 to the 21 molecules of HCl. And I'm just going to assume molecules, you guys know that. And for each of these molecules, you need to know that you have to basically multiply the front number by the number of atoms that you're looking for. So in this case, there's 3 hydrogens, so you'd have to multiply that by 3. And in the HCl, there's, again, 1 hydrogen. So that would just be 1 times 1.2 times 10 to the 21st. And if you multiply these together, that would just be 4 times the said value, which is just 4.8 times 10 to the 21st. And I believe that is answer choice C. And that is the correct answer. All right. So those are the first 11 questions, and we're going to come back to these later. So again, if you want to try these on your own, May, June 2020, again, you only have an hour for 40 questions. So you don't have that much time. Like, it's more than you might think, because again, that's what, a minute and a half per question. So it seems like a lot, but when you're doing questions such as, where is it? This one, this one might take more than a minute and a half. So just be careful. This one too, there's a lot of calculations. This one especially, I think this one took me the most time, number 10. But yeah, so pacing is a big problem. And yeah, again, when you're actually taking the test, you probably don't want to check all these. You just want to find the one and then move on. But that was that first 11 questions done. We'll come back to this later. And yeah, that's it for today. I'll see you guys later.